This week in lab, we are doing the synthesis of 1-bromobutane. We're going to make that from an alcohol. Now, if we take an alcohol and were to react with, say, sodium bromide, we would get no reaction. This is because an OH group is a 4 leaving group. Now we are going to start with an alcohol this week. We're going to use 1-butanol. And we are going to react with sodium bromide. But we're going to make a change here. We'd have no reaction if we just use sodium bromide. We're going to put sulfuric acid in there as well. And that acid is required to get the reaction to work. Now this will give us the 1-bromobutane. And that's our final product. Let's take a look at what is going on here. We'll take a look at the mechanism. Sodium bromide and sulfuric acid. This is a very strong acid, the sulfuric is. Sodium bromide is going to have to be the base. Bromide will come and get a proton off of our acid. And we make HBr. This is a strong acid itself, but it's weaker than sulfuric. Acid-base reactions, there's some equilibrium, but the equilibrium is going to favor the side of the weaker acid and the weaker base. So we're making HBr in the reaction. Now you can buy HBr, we could add HBr in directly, but it's really nasty to work with. Sulfuric is bad enough, but HBr is really nasty to deal with. So we're going to make HBr in the same vessel that we're going to react, that we have the alcohol in that we're going to react with. So it's the HBr that's actually going to be reacting here. Now again, it is a strong acid itself, it's just not as strong as sulfuric. So anytime we see a strong acid, we look for something to protonate. And we're going to protonate the alcohol. Now what we've accomplished is that we have turned a poor leaving group into a good leaving group. We have water that is a good leaving group. So to finish out the reaction, the bromine anion is going to do an SN2 substitution. Going to attack the carbon with the good leaving group and kick the water off, kick our leaving group off. And that gives us the 1-bromobutane. So there is the mechanism for our reaction this week. Now, as we know with any of the substitution or elimination reactions, we always get some side reactions as well. They're always competing with one another. Substitution, elimination, they're all competing. Let me show you some of the possible side products. So this is our major product. One possible side product is if the alcohol could react as a nucleophile and do substitution. So we have the protonated alcohol. Instead of the bromine anion attacking and kicking off the water, it could be another alcohol attack and kick off the water. I'm going to switch over to bottom line formula. It's getting too much to draw out. Now to finish this out, we just had kicked off water. Water can act as the base to pull off the extra proton. Just an acid-base reaction. And we've made an ether. So that's a possible side product. It's going to be a minor product. You're not going to have a huge amount of it because the bromine anion is a better nucleophile than an alcohol. Neutral nucleophiles are always weak, but it is a possibility. So there could be a small amount of the ether in there. Another possible side product if we take the protonated alcohol, react with water, water can act as a base, and it can pull off a beta hydrogen. Alpha is where our leaving group is, next one else beta. Water comes and grabs a beta hydrogen, electrons kick toward the alpha position, form a double bond, and kick the leaving group off. Then we get an alkene as a byproduct. So that's another possible product that we can get. Again, it would be very minor. Our bromobutane is the major product, but that is still another possible side product. And then we can also, of course, have unreacted alcohol, maybe not all of it reacted. So there's lots of possible contaminants in there, and we'll purify it. I'll tell you later how we're going to purify, get rid of these, either the alkene, ether, or any unreacted starting material that might be in there. Let's take a look at the procedure. So we are starting off with sodium bromide dissolved into water, and then to that we're going to add the 1-butanol. This will all be in your 5 milliliter round, long-necked, round-bottom flask. You'll add a boiling stone, and very carefully we're going to add in sulfuric acid, drop-wise. Notice that it says drop-wise. So slowly add a few drops, swirl it a little bit, let it mix up, add a few more drops, swirl it. So slowly add the concentrated sulfuric acid. You're going to fit the flask with a distillation head. So we're going to set it up as if it were simple distillation. Now, the procedure in the third step says to wrap the neck of the distillation head with a wet paper towel. So we're going to put a wet paper towel around the outside here. So that we can reflux the mixture. We're going to reflux for 45 minutes. So the solution that's in here is we're going to heat it to boiling. We want it to boil. It's going to come up and then hit the cooler surface where we have the wet paper towel. It will condense and fall back in. That's reflux. Reflux is boiling with return of the condensate back to the original flask. Distillation is boiling with collection of the condensate in a separate vessel. But we're going to reflux. We're going to reflux for 45 minutes. Now, the reason that we're refluxing, last week we didn't have to do this. The lab that we had last week, we didn't have to put the wet paper towel. We just distilled over because the product had a much lower boiling point than the starting material. So as it formed, the product is what distilled over. But in this week's lab, the starting material has a boiling point of 118 degrees Celsius. The product has a boiling point of 101.6 degrees Celsius. You might say, well, why can't we just distill out the product as it forms? It is low enough. If you were to do fractional distillation, we should be able to separate those. But the problem is that the alcohol and water that is being formed in the reaction, so water, let me just write it down here, the butanol and the water, they form an azeotrope, and if you recall, an azeotrope is something that boils at a temperature lower than either of the pure components. So butanol boils at 118, water of course boils at 100. But the azeotrope, its boiling point is 92.4 degrees Celsius. So if we were to just distill out, do a distillation during the reaction without allowing it to fully form all the 1-butanol, the unreacted alcohol would azeotrope out with water because its boiling point is lower than either of those components. So this is what's going to boil out first. So that's why we're doing the reflux. We're giving it 45 minutes to where all the alcohol can go to the bromobutane, and so that we shouldn't have the azeotrope occurring. Shouldn't have much that could occur. They might be a little unreacted alcohol. We're trying to get it all to go as much as possible to the 1-bromobutane, and then we will do our distillation. So after the 45 minutes, you'll take the wet paper towel off. You'll wrap this with foil. And remember, we always do a little cone with the foil. And we will allow the 1-bromobutane to distill over. Now you'll get the byproducts as well that will come over as well. If there's any unreacted alcohol, that's going to go over as well. We'll get the byproduct ether, the alkene byproduct, and our 1-bromobutane. May even be a little sulfuric acid even distill over. So there's going to be a lot of mixture in there. So once we get our distillation finished, we're going to take the vial, we're going to do some workup on that. In the meantime, go ahead and clean out the distillation apparatus, and we're going to use it again later. We're going to do a second distillation, and the procedure tells you how to clean that out. So, step 8, we are adding 1 milliliter of concentrated sulfuric acid to the distillate. Now, why are we putting all the acid in here at this point? Now, in the beginning, we added sulfuric to make the HBr. We added sulfuric with sodium bromide to make HBr. Why are we putting sulfuric into our vial that contains our product? Well, the reason is to get rid of the impurities. If there's any ether in there, you add sulfuric. You always look for something to protonate. We're going to protonate that oxygen. We lifted HSO4 minus as well. This is a salt, which is water soluble. So that goes into the water layer. If you happen to have any of the alkene byproduct, strong acid, look for something to protonate. We're going to protonate the double bond. Again, water soluble. If there's any unreacted alcohol in there, again, look for something to protonate. We protonate the alcohol. Again, water soluble. Now, bromobutane, there's nothing we can protonate on it. So that stays the organic layer. All these others, these byproducts or any unreacted starting material, will go into the water layer. So the purpose of adding the sulfuric acid to the distillate at this point is to get rid of all the byproducts and unreacted starting material. Now you'll separate those layers, and then we're going to wash the organic layer, the 1-bromobutane, with 1 milliliter of 3 molar sodium hydroxide. And that's just, the purpose of that is just to get rid of any acid that may still be around. We don't want any acid in with our product. You'll take the bromobutane layer, which will be the bottom layer, put that into a new reaction tube and dry it over anhydrous calcium chloride pellets. Now, we're going to do a, after you've given it time to dry over the pellets, we're going to take and put it back into our distillation setup. So our long-necked, round-bottomed flask. We'll put the 1-bromobutane into the flask. Put a boiling chip in the flask, and then in the neck of the flask, we're going to put into the neck some steel sponge. Whoop, I forgot one. Before you put the steel sponge, just a second. You'll put the 1-bromobutane in. You're going to wash the calcium chloride pellets with p-xylene also called paraxylene. This is the structure of p-xylene. It's a benzene ring with two methyl groups on it, and they're on opposite sides. This has a very high boiling point. I don't have it written down. Has an extremely high boiling point. And we're going to take that into liquid. We're going to wash our calcium chloride pellets and then put that in here as well. So that's washing to make certain we get any bromobutane off the pellets and into a round-bottomed flask. It says to do that twice. You're going to do 2 1 milliliter portions of the p-xylene. Oh, it's got the boiling point in the procedure. So it says 137 to 138. Not as high as I thought it was, but it's still a high boiling point. So you're going to wash our pellet. You're going to wash the pellet twice and put that p-xylene into the flask as well. So we've got the 1-bromobutane and the p-xylene. Now, the p-xylene has another purpose rather than just washing the pellets. It's got another purpose, and I'll tell you in just a moment. So in the neck of the round bottom flask, you're going to put steel sponge. Make certain there's not a piece hanging out when you put the connector on. Use the Viton connector. Make certain you don't have a piece of the sponge hanging out. If you do, you put the connector on there and that gives it a place to leak. So you have a thermometer in the top, and we will collect into a pre-weighed vial. This will be in ice. We'll weigh the vial ahead of time, and so that we can calculate a percent yield. Now, we're going to heat this up to boiling. We want to distill over the 1-bromobutane. So it's going to come up, steel sponge giving us greater surface area, giving us more theoretical plates, so we can get better separation. Now, hopefully your 1-bromobutane is very, very dry. When you dried it with the calcium chloride pellets, make certain you give it plenty of time to get dry, because the boiling point of that 1-bromobutane was 101.6. Boiling point of water is 100. So if you got some water in there, it's going to distill over as well. So make certain you dry extremely well with the pellets. Give it plenty of time to get good and dry, because it will just if there's any water present at this time, it will distill with the 1-bromobutane. Now, as the 1-bromobutane distills up, we don't have much. We're working on a very small scale here, where you're not going to get much product. You can't afford to have some stuck on the steel sponge. We want all the product to get over so we can get as good a yield as possible. That's the other purpose of the p-xylene, paraxylene. This is called a chaser solvent. It's a solvent that has a higher boiling point than the compound that you're trying to distill, and it's going to chase it up the column, up the steel sponge, and over into your vial. Because when the p-xylene comes up, if there's any 1-bromobutane still on the steel sponge, when that p-xylene hits it, as it starts to distill up, it's got a higher boiling point, it's going to be at a higher temperature. It will instantly vaporize any 1-bromobutane and help chase it over. That's why we call it a chaser solvent. Now, you want to be very, very careful with your temperature when you're distilling. The distillation, it says there, should only take place between 99 and 103 degrees. That is just the product. You get it too high, let the temperature rise up too high, you're going to be getting some p-xylene over, paraxylene. We don't want the paraxylene. If you happen to distill some paraxylene, it will show up in the IR spectra. So we don't want any of the p-xylene. But it's, excuse me, again, its purpose is to chase our solvent, chase our product over so we can get a better yield. So weigh your product, calculate a percent yield. I showed you last week how to do a percent yield. And then you will take an IR of your product. I will give you an IR of the starting material, and you can compare the two. Again, talk about any peaks that disappear or appear. Also talk about your purity of your product. That IR will show if you have any unreacted alcohol or any of the p-xylene that you happen to distill over. We shouldn't distill any over, but if you let the temperature get too hot, you go too fast and let the temperature get too hot, you could get some to distill over, and we'll see that. Okay, now I think that's all I need to talk about on this week's lab. Next Monday, we have our lab final exam. Monday night, 6 o'clock, in your normal assigned room. So let's talk about a little bit about what's going to be on the exam. Let's see, I start off the exam with some questions about the lab that we're doing this week. I've got 5 questions on this particular lab. Much of the questions is why you're doing certain things. So make certain you know why we've done everything that we've done. Make certain you understand how everything works and why you're doing certain things. Let's see, since the lab midterm, we've done chromatography. I've got 6 questions on chromatography, on the chromatography lab. I'll go ahead and tell you one of them. We're going to be looking at, we did TLC and column chromatography. If I give you a list of compounds, be able to tell me the order in which they would elute, both on a TLC plate and on a column during column chromatography. Tell me what is the order that they would elute. Okay, so there's 6 questions on the chromatography. Make certain you know what the purpose of everything was for, why we did certain things during that lab. This final exam is a lot of explaining why we did certain things. Many of the questions are. The other day we did SN2 versus SN1 lab. And so I've got questions on that. I already told you what I would ask on that. So it was what the whole purpose of the lab was about. I've got compounds listed, and you will tell me the order in which they would react under SN2 conditions. And then I've got a question of several compounds, got them listed out. You tell me the order they would react under SN1 conditions. So you just place them in order of their reactivity. Now we've done several reactions this semester. Make certain you understand those reactions. So we're doing an SN2 of an alcohol this week to make an alkyl halide. We did dehydration of alcohols last week. We've done SN2, SN1, and then back earlier we did acid base. We use acid base in an acid base extraction, so we use some acid base reactions. So make certain you understand those reactions. I will have some reactions on your exam. It will not be the exact same ones we did in lab, but it will be something similar to the ones that we did in lab. So I'll ask you to give me the major product. So I've got 3 of those on there. Bring a calculator with you. I see some calculations that I've put on here. Bring a calculator. So I have 2 questions from older material, and all the rest of it is things since the midterm. One of the older questions is just a gimme question. Nobody will miss that one. I'm not even going to talk about it. It's just a plain gimme question. The other old question is be able to calculate how much you would extract. If I give you distribution coefficient and all that, you had that on the midterm, so I'm going to put one of those on there again, so you'll have that calculation. Last 2 labs, this lab this week and the one last week, we're doing percent yields. I'll have a calculation of that on there. You have calculated percent yield. So, bring your calculator. You'll have 2 calculations to do. Here's another question on the SN2, SN1 lab. It's a why question. The next question here, let's see. We've got I've got 2 where I'm going backwards. So we had the reaction, so I'm giving you 3 reactions and you have to give me the product. I've got 2 questions where I give you the product and you have to give me the starting materials. You would have to tell me what starting materials we would use to make those products. So you're going backwards. I give you the product, you give me the starting materials. We covered IR spectroscopy. You already know what to expect on that. I've got several IR spectra, and you will match the compound to its spectra. So it's just a matching is that question. You got 4 spectra, and let's see, I've got 7 compounds, and you tell me which compound gave the spectra. So there's 3 that you won't use. And that's it. That's the lab final. So again, the majority of the questions will be things since the midterm. I've only got 2 questions that were before the midterm. One is calculation of the amount that you would extract, and the other one, like I said, it's just a gimme question. Everybody will get it right. Okay.